It is 2.00 a.m. Your script runs, your local LLM outputs this brilliant, perfectly formatted response, and you lean back in your chair thinking you have crossed the finish line.
Yeah, best feeling in the world.
Right. But for a software engineer getting into AI for the first time, a successful local deployment isn't the finish line. It is, well, it's a trap.
A massive trap.
Welcome to our deep dive into the realities of monitoring AI in production. I'm your host, and today we are looking at exactly what happens after an LLM system goes live and why your traditional software engineering instincts will leave you entirely vulnerable.
And I'm the expert joining you today, and I can tell you firsthand what works on localhost almost never survives the collision with real-world production data.
Okay, let's unpack this. We have a stack of notes here on monitoring in production, and the core problem we need to confront right away is the reality of how AI systems fail compared to traditional software. Because before we can fix a problem,
You have to actually understand it.
right, exactly. We have to understand how fundamentally different an AI outage is from a standard web app outage. Because, as engineers, we are conditioned to expect violent, immediate failures.
Loud failure.
Yes, loud. Traditional software bugs are like a car engine throwing a rod. You get an immediate 500 server error, your pager triggers, and you get an explicit stack trace pointing you right to like line 42 of your code base where a null pointer exception occurred. The system is objectively broken.
It's binary. But LLM systems, they fail silently. Without active observability built in from day one, the degradation of an AI system is gradual. It's completely invisible to your standard APM tool.
Invisible, like Datadog won't catch it.
Datadog will tell you the server is running. But what's fascinating here is because of the shift from deterministic programming to probabilistic programming, broken becomes a subjective spectrum rather than a binary state.
Yeah, because in traditional software, if you give a function the exact same input, you get the exact same output
Yeah.
every single time.
Exactly. An LLM, though, is calculating the probability of the next token in a sequence based on vast amounts of data and weights. So you don't get a syntax error. You get an output that is, a little less helpful, a little more generic, or one that subtly hallucinates a fact that sounds completely plausible.
Oh, man. So to your traditional server metrics, everything looks perfectly healthy.
Yep. CPU usage is fine, memory is stable, network traffic is flowing perfectly smoothly.
It's less like a server crash and more like memory fragmentation.
Yeah.
The system just keeps running. The HTTP endpoints keep returning 200 OK statuses, but the relevance of the output just gets increasingly scattered until it's effectively useless.
Yeah, that's a great analogy.
Like you are getting a 200 OK response that confidently tells your user to put glue on their pizza to keep the cheese from sliding off.
Right. The server did its job flawlessly.
But the product failed catastrophically.
Precisely. So if the infrastructure is perfectly healthy, but the output is degrading into that memory fragmentation state, what is actually causing the shift? Well, our sources identify two primary culprits here: data drift and model drift.
Okay, great.
Yeah, and they represent two fundamentally different ways the ground can shift beneath your application's feet, and they require completely different detection strategies.
Wait, I have to push back on this on behalf of the listener. If I deploy a frozen model, let's say I download an open source model, right? I put the weights on my own server. I do not update them. I literally freeze the code and the mathematical weights. How on earth does it drift?
Because the world around it changes. I mean, think about it. Your users start asking slightly different questions. A new slang term trends on social media, a competitor launches a new product, or, a new software framework gets released.
Ah, okay.
Your users start inputting data that looks structurally or thematically different from the data your model was originally evaluated on.
But shouldn't my prompt engineering handle that? Like if I have strict system prompts, something like only answer based on this provided context and say you don't know otherwise, should it just reject things that fall outside its training?
Well, in a perfect deterministic world, yes. But LLMs are inherently probabilistic, and frankly, they are people pleasers.
People pleasers, I love that.
They are heavily optimized to provide an answer. So when users start asking about a new JavaScript framework that was literally released yesterday, the model might try to extrapolate or synthesize an answer based on older, irrelevant patterns. The model is behaving exactly as programmed, but its responses are no longer accurate for the new context of the real world. That is data drift.
So it's not the model degrading, it's the input context outgrowing the model's static knowledge base.
Exactly.
But how does a software engineer actually detect that before a user complains? I mean, we can't just sit there and read every single incoming prompt.
No, you'd go crazy. You measure it programmatically using embedding distance. You convert the incoming user prompts into vector embeddings, and you map them in a multidimensional space against the embeddings of your original evaluation dataset.
Oh, wow. So it's pure math.
Pure math.
Huh.
If the statistical distance between those live vectors and your baseline vectors starts growing over time, your users have drifted. The semantic space your app is operating in has fundamentally shifted.
Okay, that makes perfect sense for a frozen, self-hosted model. But what about the second culprit? Model drift.
So model drift occurs when you are relying on a third-party API from a major provider. You might have your prompts perfectly tuned to a specific version of their model, but, these providers are constantly tweaking things behind the scenes.
Right, without telling us.
Exactly. They implement new safety guardrails, they run silent background optimizations to reduce their compute costs, they adjust the alignment. Suddenly, the exact same prompt that yielded a really highly creative, nuanced answer on Tuesday yields a rigid, generic refusal on Thursday.
You are building a house on a foundation that reshapes itself in the middle of the night.
Yep.
You didn't touch your code, the users didn't change their behavior, but the model shifted underneath you. So if we know these failures are silent, and we know they are driven by either the input data drifting or the upstream model drifting, how do we build a defense mechanism?
The sources outline a very specific framework. To catch these invisible failures, you have to establish 5 pillars of monitoring: quality, latency, cost, errors, and safety.
5 pillars: quality, latency, cost, errors, safety. Got it.
You need dedicated observability for each one, because missing any single pillar creates a blind spot that will inevitably take your system down.
Here's where it gets really interesting for me, especially when we look at that third pillar, cost.
Yeah.
In traditional web development, you rarely monitor cost in real time.
No, never. You just look at your AWS bill at the end of the month and cry.
Right. You wince at the invoice. A bug in your code usually just means a feature doesn't work or a process crashes. But with LLMs, you are paying per token. The financial risk is immediate. It's tied directly to the code's real-time behavior.
An infinite loop in a traditional app crashes the thread. An infinite loop in an LLM agent where, say, it encounters an edge case, queries the API, generates tokens, feeds those tokens back into its own prompt, and queries again. It doesn't just crash a server, it racks up astronomical API bills instantly.
Oh, that is terrifying.
It is. A logic bug in an autonomous agent isn't just a bad user experience. It is a financial hemorrhage occurring at the speed of compute. You can burn through thousands of dollars in a weekend if a retry loop lacks a hard circuit breaker.
Which naturally leads us to the errors pillar, because in standard web apps, we just monitor 404s and 500s. But LLM errors are an entirely different beast, aren't they?
Totally different. We are looking at context window overflows because a user tried to paste a 50-page PDF into a prompt designed for a single paragraph. We are looking at rate limits from the provider. We are looking at malformed JSON outputs where the model just, forgets a trailing comma and completely breaks our downstream deserializer.
And those downstream breakages are deeply tied to the latency pillar, right? Because latency in an LLM system isn't just network round-trip time. You have to monitor time to first token, or TTFT, versus total generation time.
Yes. If we connect this to the bigger picture, you can see how these pillars constantly pull against each other.
How so?
Well, let's say your latency is too high, so you switch to a smaller, faster model.
Makes sense.
You solve the latency issue and you lower your cost pillar simultaneously. Win-win, right?
Sounds like it.
But suddenly your errors spike because the smaller model isn't smart enough to maintain strict JSON formatting, or worse, your safety and quality pillars collapse.
Safety and quality. These feel like the hardest ones for an automation-obsessed engineer to grasp, like setting up dashboards for TTFT, token costs, and API timeouts. That's straightforward. We have Datadog and Prometheus for that. But how do you write a regex to detect if a model's response is subtly passive-aggressive? Or if it's giving technically accurate but contextually dangerous advice?
Well, you can. You can use automated proxy models, like using an LLM as a judge, to evaluate another LLM's output for semantic similarity to a known good answer.
Right, LLM as a judge is getting popular.
It is, but the sources are explicit here. The ultimate safety net is not automated. It requires human review.
Wait, really? It sounds like we're just telling highly paid engineers to sit down with a cup of coffee and read logs. It feels like a massive step backward into manual labor.
It's much more rigorous than simply reading logs. We are talking about qualitative auditing, or human-in-the-loop evaluation. When you sit down with that sample of production data, you aren't just browsing. You are grading. You are performing manual data annotation. You are establishing a baseline of ground truth. Automated evaluators can tell you if the text contains the factual answer, but only a human embedded in the specific context of your business can tell you if the tone, the nuance, and the alignment are actually hitting the mark.
You are managing the personality of your application.
Yes.
Because no dashboard is going to flash red because the customer service bot sounded slightly condescending. The latency was low, the token cost was minimal, the JSON parsed perfectly. But the user left the interaction feeling vaguely annoyed.
And then subtle annoyance is exactly how you lose a user base over a 6-month period.
Yeah, death by 1,000 cuts.
This is why the sources insist that qualitative auditing cannot be an ad hoc chore you do when you have free time. It has to be a scheduled engineering ritual. You pull a statistically significant sample of the week's inputs and outputs, and you bring them.
And I guess this feeds back into your automated evaluation pipelines, constantly calibrating your proxy metrics against actual human judgment.
Exactly.
So let's play out the nightmare scenario. You are doing your weekly qualitative audit, you are looking at the data, and you realize the model has gone completely off the rails.
Oh, no.
Yeah, it has suffered severe model drift, the provider changed something under the hood, and your application is currently giving terrible brand-damaging advice to live users right now. What is the next step?
This separates the mature engineering teams from the amateurs. You need a pre-built incident response playbook with architectural rollback mechanisms ready before they are ever needed.
Reform.
Yes, before. When an LLM goes rogue in production, time is your enemy. The scale at which these models can generate poor interactions is staggering. You do not have the luxury of opening up a Slack huddle to brainstorm how to fix the prompt or trying to quickly fine-tune a patch.
Right. When the house is on fire, you don't start drawing up blueprints for a fire extinguisher. You need to know exactly which lever to pull. But from a systems architecture standpoint, what does that lever actually look like?
You need an LLM gateway pattern. Your application shouldn't talk directly to the model provider. It should talk to an internal gateway. And within that gateway, you configure circuit breaker patterns.
Okay, so if the primary model starts throwing rate limits, or if our automated safety evaluators flag more than, say, 5% of responses in a 1-minute window, the circuit breaker trips.
Precisely. And the playbook dictates what happens next. The gateway automatically routes traffic to a smaller, faster fallback model. Or, if you use shadow deployments, you can instantly revert the routing to a previous older model version that you know is stable.
But we have to be careful there, right? If you auto-fail over to a smaller model to mitigate a crisis, you have to know how that affects your downstream parsing.
Oh, absolutely.
Like we discussed earlier, a smaller model might return the answer faster and stop the timeout errors. But if it drops your strict schema requirements, you've just traded a latency bug for a catastrophic syntax error in your application pipeline.
Which is why sometimes the most effective circuit breaker isn't another LLM at all.
What do you mean?
If the entire generative pipeline is compromised, the gateway might flip to a hard-coded fallback response, like, "We're experiencing high volume, please call our support line." Or it might bypass generation entirely and fall back to a traditional semantic search index, serving static, pre-approved documents.
Ah, so you just shut off the AI completely.
Right.
The technical implementation is crucial, but the organizational discipline is what really makes it work. These decisions like what triggers the circuit breaker, which fallback model to use, who is authorized to manually trigger a shadow deployment rollback, those have to be made in the calm of a Tuesday afternoon planning meeting, not in the panic of a Friday night outage.
It is a profound shift in how we think about software maintenance. You are no longer just deploying static logic. You are operating a dynamic, probabilistic system that interacts with an unpredictable world. It requires a totally different set of architectural patterns and a much higher degree of active vigilance.
So to synthesize this entire journey we've been on, you deploy your model locally, and it works. You cross that starting line. But immediately, you have to architect your production environment for the invisible threat, which is silent failures.
Yeah.
No more waiting for stack traces.
Yeah.
You have to actively look for degradation using vector embedding distances because a 200 OK means absolutely nothing about the semantic quality of the output.
Nothing at all. You build your fortress on the 5 pillars, tracking the quality of the output, optimizing time to first token for latency, implementing hard limits for costs,
Got to watch those infinite loops.
catching context overflows for errors, and actively auditing for safety. You balance them knowing that adjusting one slider inevitably impacts the others.
And finally, you embrace the unautomated truth. You schedule your weekly human-in-the-loop qualitative audits to catch the subtle failures that math just can't see, and you implement your LLM gateways and circuit breakers so you are never caught empty-handed when the underlying model drifts beneath you.
It is a lot to manage, but the good news is we are going to put all of this theory into practice. Tomorrow, our deep dive shifts into the Building Apps module.
Yes. Now that we understand the risks and the heavy architectural requirements for monitoring, we're going to construct a real text generation application from scratch. We're going to cover everything from choosing the right API to handling those streaming chunk responses so your PTFT stays low, all the way to deploying the finished product behind a robust gateway. It's going to be incredibly hands-on.
Building these systems is where the real engineering challenge lies, especially when you know you have the observability safety nets we discussed today firmly in place.
But before we sign off, I want to leave you with something to ponder late into the night. The next time you are sitting in the glow of your monitor, watching a model stream text onto the screen, think about the paradigm shift we just explored. If our models constantly drift because the world around them changes, and if we have to continuously monitor their behavior, audit their output for tone and alignment, and course correct them based on subtle nuances in their performance,
Yeah.
at what point are we software engineers no longer just maintaining a piece of code, but actually acting as managers for a digital employee? Keep coding, keep questioning, and we will see you tomorrow.